Good afternoon, I'm Chris Cox, and today I'll be presenting a summary of our paper, Improving Mixed Reality Prototyping Through a Classification and Characterization of Fidelity. In this paper, we explore how a classification of the dimensions of prototype fidelity can help us to design new prototypes more effectively. This is done through the proposal of a taxonomy of prototype fidelity, identifying the different dimensions of a product that can be emulated through mixed reality prototyping. Over the last decade, mixed reality technology has had a massive increase in capability and popularity. Tools such as virtual and mixed reality headsets, augmented reality, and haptic gloves are becoming widely available, and applications such as Pokemon Go and Amazon's AR View have truly thrust this concept into the public eye. By combining the flexibility and replicability of the virtual domain with the validity and tangibility of the physical domain, mixed reality offers an exciting tool for prototyping that can utilize the benefits of both domains. However, mixed reality covers a broad spectrum, from augmented reality to augmented virtuality, as described by Milgram and Kashino. Identifying where along this continuum to locate a prototype is not a trivial task, and will depend on the purpose and form of that prototype. Another key decision that must be made before creating a prototype is what level of fidelity is required. Fidelity is often quoted on a simple scale of low to high. However, this spectrum fails to capture a lot of detail, and its subjectivity can make the distinction between high and low fidelity difficult to discern. To further complicate the problem, when using mixed reality prototypes, we must consider the fidelity of the virtual elements as well. Using this methodology to categorize the fidelity of a mixed reality prototype is difficult and often unhelpful. For example, here are three different mixed reality prototypes of the same cordless electric drill. The first is a projection of a digital representation of the drill onto a physical marker when viewed through a camera. The second uses the Spark platform to project a virtual color map onto a blank 3D representation of the drill. The last example uses a virtual reality headset to project a fully colored virtual version of the drill over the position of the blank 3D representation, which can be interacted with. These prototypes would be difficult to place on the two-dimensional spectrum of fidelity previously described, as they all have elements of both high and low fidelity. As such, we propose that a clearer definition of fidelity may come from separating out the different components of fidelity based on how we perceive prototypes. This means that instead of a simple high and low scale, fidelity could be expressed as a profile across these dimensions. To break fidelity down into its constituent components, we've taken the taxonomy of mixed reality proposed by Fink and Schreiber, splitting it into three categories: physical, functional, and psychological. The physical dimension is defined as the extent to which a prototype duplicates the appearance and feel of the object it is representing. The functional dimension covers the extent to which a prototype responds to user inputs, operates, and duplicates stimuli present in the operational environment of the prototype in the same way as the object is representing. The psychological dimension is slightly more abstract and is defined as the extent to which the user perceives the prototype to be an exact duplicate of what it is representing, and therefore behaves and interacts with it as they would the real product. Within these three main categories, we've identified a number of subdimensions that can be used to further specify the exact fidelity profile of a mixed reality prototype. Within the physical dimension, we break down the subcomponents of the haptic and visual categories that make up the appearance and feel of a prototype. Within the functional dimension, the way in which a prototype operates and responds to user inputs is broken down, as well as the way in which the prototype emulates the stimuli in the operational environment of its intended use. Finally, within the psychological dimension, the two key aspects of user presence and agency are highlighted, as well as the importance of representative behavior. By breaking down fidelity into these components, it is much easier to evaluate the fidelity profile of a prototype and to create a clearer target of fidelity for a prototype that is being created. One of the reasons for creating this taxonomy was so that it can be used as a tool to help identify the key characteristics of a mixed reality prototype that should be designed for, based on the requirements of that prototype. Depending on the purpose and the use case of a prototype, some dimensions of fidelity will be more important than others, but creating a comprehensive mapping from all the different types of prototypes, prototyping methods, and prototyping goals to the most important dimensions of fidelity would be a mammoth task. So instead, a case-by-case process is proposed so that designers can identify what dimensions of fidelity are the most important for their specific prototype, and what levels of fidelity are required. This process starts by reviewing the Taxonomy of Fidelity and identifying the key dimensions based on the prototype characteristics. Based on this, the required fidelity levels can be chosen, the virtual and physical components of the prototype can be created, and the prototype can be evaluated according to its purpose. By following this pipeline, prototypes can be made to exactly the required fidelity, with extra time and resources not wasted developing aspects of the prototype that are less important. To summarize, as mentioned previously, a clearer understanding of the required fidelity profile of a prototype will lead to more efficient prototyping. Additionally, the language used in this taxonomy could also be used to assist communication when evaluating the prototype. Another key opportunity that requires further investigation is the potential to use the virtual domain to influence the user's perception of a prototype. There has already been some work to show that the visual cues of the virtual domain can influence the user's perception of the physical domain. This is still a largely unexplored field, especially within prototyping, but it offers the ability to make instantaneous virtual changes with perceived effects in the physical domain, potentially speeding up design iteration. Some of the key challenges that face this research include quantifying the fidelity within each of these dimensions. While it is valuable to identify the different dimensions of fidelity themselves, it will be necessary to clarify what high and low fidelity actually mean within each dimension. Another challenge will be creating an easily digestible way of presenting the overall fidelity level of a mixed reality prototype. One solution to this could be to use radar plots to create a fidelity map of sorts, though further work is required to test this. And finally, the importance of the different dimensions of fidelity should be investigated. Different product classes and types of prototype will depend on different dimensions of fidelity, and these relationships need further investigation in order to fully understand how best to use mixed reality prototypes. Thank you very much for listening. Any questions would be welcome.